So I see the second speaker is ready. So it will be Giacomo Tendas from Macquarie University, who will tell us about flat versus filtered colimits in the enriched context.
Thank you very much for the introduction. And can you all hear me? Okay, so let me also thank the organizers and the scientific committee for allowing me to give a talk at this conference. It's really great to be even virtually there. So today I'm going to talk about joint work with my supervisor, Steve Luck. And all that I'm going to say today is already on a preprint that it's on arXiv and goes by the same title as this talk, like the complete title being Flat versus Filtered Colimits in the Enriched Context. So as the title says, what I want to talk about is a comparison between the flat functors of enriched categories and filtered colimits. So the aim is to characterize these flat functors as filtered colimits of representables, as it happens for usually category theory. And the motivation for these results is a better, if you want, a better understanding of the theory of enriched accessible categories. So let me start simply by recalling some facts about ordinary accessible categories, and maybe let's start with some history. We can say that all kind of began in 1978 when Ereshman introduced the notion of a sketch and models of a sketch as a nice way to present categories, and a nice way to present really nice categories. Then the theory developed and it became more famous when Gabriel and Ulmer gave a characterization of some of these sketches, the so-called limit sketches, and this happened in 1971. And they characterized these as what we now call locally presentable categories, which is a very nice way of presenting them. And finally, we arrived to the theory of accessible categories only in the 80s, with the contribution of Lair and Mackay and Paré independently that discovered this notion as that characterizes the models of general sketches introduced by Ereshman. Here on the left, you find a sequence of examples of accessible categories in increasing order. Every pre-sheaf category, every Grothendieck topos. Of course, every locally presentable category is accessible. And as I just mentioned, the category of models of sketches are all the accessible categories. So that's all of the examples if you want, as well as all categories of models of first order theories. So as you can see, the range of examples is very wide, and many categories that you encounter, that you meet in your journey is probably accessible. And also they have many properties, good properties. Here is a list of some of them. So they have certainly a small and dense generator, which is that even more than that, it's a generator that generates under alpha filtered colimits for some alpha. And they are complete if and only if co-complete. And they're also stable under all flexible limits in CATs, so in particular under pseudo and bi limits. And they are kind of the right setting for when you want to prove adjoint factor theorems or weak adjoint factor theorems. And these are only a few of the many properties studied and related to accessibility. So how is accessibility related to the notion of flatness? So let's see what we can say as the definition. So I'm going to focus about what we call finitely accessible category. There is, of course, an infinitary version, but for this talk, we stick to that. So we can try to define finitely accessible category by proposition, if you want. The following two conditions are equivalent for a category A. One, A is the free co-completion of a small category under filtered colimits. And two, A is equivalent to the category of flat pre-sheaves on a small category C. So if either of those hold, we say that our category is finitely accessible. And usually the one that is taken as definition is the first one, and the second is just an equivalent characterization. Okay, so this is two equivalent characterization of the same thing. let's see what are the pros and cons of them. The first approach is really useful when you want, for example, to recognize that a category is finitely accessible, because it tells you that A is finitely accessible if and only if you can find a small full subcategory made of finitely presentable objects. So this means that when you ohm out of your object, that's a finitary functor, meaning that it preserves filtered colimits. And this small subcategory generates your category under filtered colimits. So that's a nice intrinsic definition that allows you to check whether a category is finitely accessible or not. While the second notion, that involving flatness, is really useful for the development of the theory. In fact, it is thanks to the second approach that one can prove that a category is accessible, so the infinitary version of it, if and only if it's the category of models of a sketch, and if and only if it's the category of models of a first-order theory. So what makes the theory of accessible categories so nice? I mean, it's not just this, but a big important thing is that this equivalence hold. And so what we want to do is to consider the enriched setting and consider when this equivalence holds as well. And when it doesn't, what can we do? Okay, but it's too soon. Let's not go to the enriched setting yet. Let's talk a little bit about flatness, because I haven't said yet what it means to be flat for a functor. Well, again, let's define flatness by equivalent definitions. So if M is from C up to set is a presheaf, we say that it is flat if it satisfies one of the three conditions here. So either the category of elements is filtered, or M is itself a filtered colimit of representable functors, or the left-Kan extension of M along Yoneda preserves finite limits. So the third one is what, in my head at least, is what it should be the definition of flat functors, and also what it will be the definition of flat functor in the enriched setting. And so the equivalence of 3 with the other two is what allows you to prove the equivalences in the previous slide, and so the relation between the two notions of accessibility. Also, I want to point out something that will be relevant later. Every flat functor can be written canonically as a filtered colimit of representable just by using the fact that every functor is the colimit indexed on its category of elements, and that by 1, this is filtered. Okay, so and this is all I wanted to say about flatness in the ordinary setting. Next, we move to the enriched context, and I don't really want to say much about this, just a few things. So probably many people will be familiar, at least with some kind of enrichment. So the idea is that you replace ohm sets with an object which lives in a symmetric monoidal closed category. So, for example, if you are a two-category theorist, think about two categories as those enriched over cat. Or if you are a simplicial person, think about simplicial categories as those enriched over simplicial set, and so on. Additive categories are those enriched over AB. Then you have the G categories, or even the notion of Liouville metric space, which is that enriched over the monoidal category of the real numbers. What I want you to know about enrichment, if you don't know much, is just that you can do ordinary category theory. So you have the notion of functor between enriched category of V-natural transformation. You have categories, V categories of V functors, and you have Yoneda embedding. Pretty much you can recover all of the theory of an ordinary category theory, including limits and colimits. Here, the notion of limits and colimits is generalized to that of weighted limits and so on. But we don't need this for this talk. So this is in general the theory of enriched categories. What we'll assume from now on is that our base of enrichment is locally finitely presentable as a closed category. So the additional part here, which was introduced by Kelly, means that the set of finitely presentable objects contains the unit and is closed under tensor product. So all the categories here, at least all of, but the last one are locally finitely presentable as a closed category. The last one is locally alpha presentable as a closed category for a bigger alpha. Okay, so let's move forward. And so we can move, once we get to the enriched context, we say, what's the right notion of accessibility one can consider? And so if we look back at the proposition at the beginning, in which we had two equivalent definitions, well, we might consider them independently, and they will provide two notions of accessibility, which unfortunately are not equivalent in general. So if we generalize the first approach, we say that a V category is conically finitely accessible if it is the free co-completion of a small V category under filtered colimits. And again, this is proper because you get a nice intrinsic definition. You can prove whether something is conically finitely accessible or not. And so it's really good to work with. And this notion has been considered in various settings, such, for example, in the two categorical context, in the context of simplicial set, as well as the context of additive categories. And this has been around for a while, probably since after the definition of locally presentable category given by Kelly in the enriched context. If we generalize the second notion, which is that involving flatness, so we say that a V category is finitely accessible if it is equivalent to the V category of flat V functors on a small V category, then we get another notion. And as it happened in the ordinary context, this is the notion which is good for the theory in the sense that then you can prove the usual theorem involving models of sketches. And this notion was introduced by Bourseau, Quintero, and Rositsky, and they proved that one can characterize accessible categories in this sense, so in the flat sense, as those that arise as models of sketches. So on the one side, we have the notion that is good to work with, and on the other side, we have the notion which is good for the theory, but it's not good to work with because in general, you don't have a nice characterization of flat functors. And they, in general, are not the same. So it's not true that one holds if and only if two holds. They holds, so the equivalent holds in the co-complete case. So that's the case of locally presentable categories, and it's always a nice setting. But today we are interested in the case in which you don't have all colimits. So what can we do in that context? Well, first of all, we can define, I should say, what flat functors, V functors are. Well, generalizing the original notion, we say that a reached presheaf is flat if its left can extension along the Yoneda preserve finite weighted limits. So what we want to do is characterize these flat V functors in terms of filtered colimits. And the strategy we'll adopt to do that is, well, to start with a flat V functors from V up to set, let's say M, take the underlying functor, let's say M0, which goes from C0 up to V0, composed with the functor that comes out of the unit, prove that that is flat, and then go back through this adjunction and prove that the co-unit is in fact invertible. And that will allow us to characterize flat V functors as filtered colimits of representables, in some cases, as we'll see. So let's try to do that. Of course, we'll need some hypothesis on V, because in general, we know that that's not true. For the first case, in which we'll prove that flat functors are just filtered colimits of representables, we give these two conditions on V. So we want that the functor V0 I blank is co-continuous. So this means that this comparison here is an isomorphism. And that strong it is strong monoidal. So again, this comparison map here induced by the tensor product of the monoidal category is an isomorphism. And this is a bunch of examples here on the right. And the two that of this list, which I think are really important, are cat and simplicial set. But there are others. So for example, 2-cat with the pseudo gray tensor product, or 2-cat even with the Cartesian one, and more generally, V-cat whenever V is locally presentable with the usual tensor product. So in particular, metric space, Liouville metric spaces. And one can do actually a bit more because you don't really need this to be isomorphisms. It's actually enough for this to be epimorphisms. And in that case, for example, you can consider something more, which is pointed sets. And the pointed version of many of these examples here. Okay, then as promised, in this setting, so under these assumptions, one can prove the following proposition, which is that if you are given a flat V functor, then the category of elements of its underlying functor defined before, UM, is filtered, and the colimit indexed on this category is actually M itself. So if you want, this is what we called before FUM in the adjunction. So this is saying that every flat V functor is a filtered colimit of representables. So as a direct consequence of this, you get that a V category A is finitely accessible if and only if it is conically finitely accessible. So the two notions coincide for all these bases of regression, which is really nice, I think. The second and last class of example I want to consider, it's what we call locally dualizable base of enrichment. And while I don't want to go through the definition, here it is on the left. Let's just maybe look at the examples. If you want, the examples are really the algebraic enrichments you can do. So commutative monoids with their tensor product abelian groups, R modules for a commutative ring, and graded abelian groups, and more generally, graded R modules graded on an abelian group G. What I want you to take from this definition is that, in particular, your base has direct sums and as a strong generator made by dualizable objects. And this is important for the next step. In fact, you can prove that the proposition from before with some additional hypothesis on your base category, which is if your C has finite direct sums and copowers by the dualizable objects just mentioned, then every flat functor out of C op can be written exactly as before, has the colimit indexed on the category of elements of its underlying functor, and that is filtered. So once again, you can write every flat functors under such a V category C as a filtered colimits of representables. So this allows you to prove a bunch of results. First of all, you can characterize absolute colimits thanks to this. So a V-cat with absolute colimits are those that are preserved by any functor. These are also called Cauchy colimits. So a V category has absolute colimits if and only if it has finite direct sums, copowers by these dualizable objects, and splittings of idempotents. Then you can characterize flatness. So already by this proposition, you get that a V functor is flat. So now your C could be any V category. You don't need those colimits. A V functor is flat if and only if it is a filtered colimits of absolute colimits of representables. And finally, the theorem involving accessibility. You have that being finitely accessible, if it is equivalent to being conically finitely accessible, and having all absolute colimits. So in this case, the two notions of accessibility are different, but not quite. They only differ from the existence of some very nice colimits. And the very last thing I want to say is that notice that it's not general. the theorem that we have here, it's not general that flat functors are generated by filtered colimits and absolute colimits. And a counterexample in a very nice base could be found by taking V to be the G sets for a finite non-trivial group G. So there is no hope to get a general characterization of flatness in these terms. And I think this is all I wanted to say. Thank you very much for your attention.
Thank you very much for this nice talk. Other questions or observations? Yes.
Thanks for your talk. You define flat functors using the Lefkan extension, and so in that case you say that the two definitions are not equivalent. What if you choose the other definition with the category of elements being filtered? Do you have the equivalence between conical accessible?
Not quite, because if you choose that as definition, in the enriched context, it's not true anymore that every V functor is the colimit indexed on its category of elements. And that's an important step in the ordinary setting that you need. So that wouldn't be quite enough to characterize flatness. You really need that preservation of these finite weighted limits, which include preservation of finite powers, which are additional to the usual conical limits that would be involved only considering the filterness of the category of elements, I think.
Yes, sorry, I meant that the category of elements is filtered, plus you have the colimit.
So in that case, you would get the equivalent definition. So you would get this if and only if, yes, but what you wouldn't get is the characterization of accessible categories models of sketches, because that requires this notion of flatness as a left-hand extension.
Okay.
But yes, if you define flatness that way, yes, you get what you would say.
Other questions? Thank you very much for your talk. I was wondering if what notion of limit you use for in the enriched setting, and if weighted limits have any role in it.
You mean like in the definition of flatness, for example?
Yes, exactly.
Yeah, so these are what Kelly defines to be the finite weight limits. So are just the usual finite conical limits plus finite powers. So powers by finitely presentable objects of V. And these finite powers are really necessary. So you need preservation of these finite powers, so this initial enriched limit. For example, when you want to write this isomorphism, you really use that preservation. So you do need conical limits plus the powers.
Thank you.
Okay, so in your first list of examples, so I was a little bit surprised not to see vector spaces, but a little later they appeared as modules over the commutative ring.
Yeah. So they appear in this example. Yes.
Our next thing to look at might be modules over a bialgebra, because that is also a monoidal category, and maybe things could work there also. Do you know it?
Yeah, is that a symmetric monoidal? But I guess it's something I could look at. So modules of a bialgebra.
It is symmetric if the bialgebra is co-commutative.
Of course.
Or triangular.
Yeah, that's something I can have a look at. Thank you.
Ciao Giacomo.
Ciao.
Did you check what is a finitely accessible metric space? I'm quite curious to see.
I haven't actually. But if you want, like, well, first of all, with metric spaces, I didn't mention it here. This is only locally Aleph1 presentable as a closed category, so you can't really consider. I mean, you can define it, but the theorems apply only at the level of Aleph1. So what I could check is what is an Aleph1 accessible category, and
Yes.
I guess thanks to this theorem is something as above, just generate another Aleph1 filtered colimits, but I haven't looked at it closely.
Okay.
Thank you.
Apparently, there's a question online.
Hi, Giacomo. Excellent talk.
Hey, thanks.
So you gave two theorems, giving circumstances in which you can relate these two possible definitions of accessible V category. And I noticed that a very important example doesn't seem to fall under either case, namely the base of enrichment being chain complexes, differential graded abelian
Yeah,
groups.
that's true.
Yeah, so what can you say about the notion of an accessible DG category? What should be the appropriate thing, or can you come up with yet a third theorem which would capture that case?
We do have a third theorem,
Okay.
actually, yes. And that's in the paper. I didn't have time to speak about that today. And so DG categories don't fall into this example of locally dualizable things. And what we do is characterize flatness in terms of what we call proto-filtered colimits and absolute colimits. And these proto-filtered colimits are those that in your DG category may not be filtered, but if you look at them in the underlying graded category are filtered. So it's something a bit messy if you want, but we do get a characterization, and then you can talk about finitely accessible categories, those generated by under these proto-filtered colimits.
Excellent.
Hope that
Thank
makes
you.
a little sense.
No, it's fascinating. Yeah.
Great. So let us thank Giacomo again.
Thank you.
We have 2-minute break.